Okay, so let's start with the last talk by Simon Vialaret. He's from Bochum, and he's going to talk to us about systolic inequalities for S1 invariant contact forms. Thank you.
Okay, thank you, Lucas. And thanks a lot for to the organizers for first inviting me and organizing also this wonderful conference. And I think since I'm the last one speaking, I think it's a good moment to give a big round of applause to the organizers, to thank them. So thank you. Okay, good. So we finished the week as we started it with some contact dynamics. I'm going to recall a few things that Alberto talked about on Monday, and then we will move to the setting of today. So contact forms. So alpha is a contact form. So on, say, a 2n plus 1 dimensional manifold, a contact form is a one form satisfying the following condition, that alpha, which d alpha to the n, is a volume form. Okay? So contact forms, they come with some friends. When you have a contact form, you have its kernel, which is the underlying, let's say, topological object supporting the contact form, and it's called the contact structure. And most importantly for us, contact form also come with a canonical flow, the rep flow. And the dynamical study of rep flows is a pretty rich topic. So the systole of a contact form, we know it already, I'm just going to recall it. It's the minimal period of closed rep orbits. Okay. So, I mean, the existence of closed rep orbits is, in general, a very difficult question. It's known in dimension 3. I mean, all the manifolds are compact here. It's known in dimension 3. It's known for a certain class of contact structures. But for today, we don't need to worry about any kind of difficulties, difficulties of this kind, because we will only work with contact forms for which is very, very easy to produce periodic orbits. So this is not going to be a problem. And we say that a class, let's say C, of contact forms satisfies, so by class I mean a subset of the set of all contact forms on my favorite manifold, a systolic inequality when there is a constant satisfying the following. So for all contact forms in the class, the systole of alpha to the right power is less than the constant, depending on the class, times the volume. Okay. So on Monday, Alberto told us that we know a few things about systolic inequalities in contact geometry. First thing, they never exist. So this is a result of Alberto, Barney, Umberto, and Pedro in dimension 3 of Murat Salam in higher dimensions. Let's just put it that way. There are no global systolic inequalities for contact forms. And this is due to ABHS and Murat Salam. Another thing that we know is that there are some local systolic inequalities around some special contact forms that are Zoll. So let's just write it like this. Let's say local systolic inequalities around Zoll contact forms. And the most recent, let's say, version of this result is due to Alberto Gabriele and Oliver Meyer. Okay, and today I want to explore a bit what's in between those two situations. No global systolic inequalities, but some local ones around some very special forms. And I will talk about some, let's say, some semi-global systolic inequality for a large enough set of contact forms. So what's the setting? Well, it's written over there, S1 invariant contact forms. So we're going to work in dimension 3. So M is going to be a closed, oriented, free manifold, endowed with a nice circle action, let's say a free circle action. So another way to describe this kind of manifold is to say that it's the total space of an oriented circle bundle over a closed oriented surface of genus G. So I'm going to write SG for surface of genus G. And those bundles, given a fixed oriented base, they are classified by just the data of one integer, the Euler number, with Euler number, and I'm going to write E for this number. So it's an integer which is 0 if and only if the bundle is trivial. Okay. And so the data of this number E and the genus of the base G determines the total space M. And on this kind of space, we're going to look at invariant contact forms. So a contact form alpha is called invariant. Is invariant. Well, if it is invariant, meaning that if I pull it back by the flow of the action, then I just get the same thing. And one synthetic way to write it is that the Lie derivative of alpha is 0, where x is the direction of the action. So f generates the action. Okay? And I'm going to give a name to the space of invariant contact forms. So, oops, omega GE will be the set of invariant, positive, I'm going to tell you what this is in a minute, positive contact forms on, well, the unique circle bundle over the surface of genus G with Euler number E. Say, let's write it like this. Okay. So that's the space I want to study today. So maybe just let's give a few examples. There are some rather trivial examples. For example, if alpha naught is Zoll, well, its red flow induces a free S1 action on the manifold, and alpha naught is, of course, invariant under its flow. And it's very specific because here the S1 action is given by a red flow, by the red flow of some contact forms. Maybe another class of example which is a bit more, I don't know, interesting, let's say, is some matrix on the sphere, which is called a matrix of revolution. You're just going to take a sphere, embedded sphere in R3, which is invariant, if I can draw it, invariant under rotation under some axis. This circle action on the sphere lifts to a free circle action on the unit tangent bundle, and the corresponding contact form is going to be invariant. And you can convince yourself that in that case, the action of the circle will never coincide with the geodesic flow. So in that sense, those examples are of different nature, let's say. Okay, and this is a Riemannian example, but of course, I mean, this is a Riemannian drawing, but you could also consider Finsler's fields of revolution to have a larger class of examples. And you can escape also this, let's say, reasonable class of examples by also doing some topological operations to create a big variety of examples. Topological operations, say. In fact, yeah, you're going to create an infinite family of examples. And in fact, in the 70s, Lutz gave a classification of S1 invariant contact structures. So classifies S1 invariant contact structures, which I'm not going to give, but the point I want to make is that thanks to this classification, we know that this space of invariant contact forms has infinitely many connected components. Each of them is big in the sense that they will have infinite diameter for any reasonable distance that you're going to put on the space of contact forms, let's say. So that's the point. Omega is big. Okay? Any questions so far? Sorry, say it again.
S1 invariant, you mean only invariant under Rebec?
No, by S1 invariant contact structure, I mean any contact structure invariant under any S1 action. They don't have anything to do with each other a priori. In particular, I mean the S1 orbits, they really don't have to stay transverse to the contact structure. Okay. Okay, so I'm going to state the first result of today, which is that almost all, let's say, invariant contact forms are going to satisfy a systolic inequality. So, theorem A. Theorem A says the following. There is a positive constant, universal constant, doesn't depend on anything, such that for all choice of genus of the base, and for all non-zero, all a number, we have the following systolic inequality on the corresponding class of invariant contact forms. So the systole of alpha square is less than this universal constant times the volume. Okay, so let's say invariant contact forms under this condition of non-triviality of the circle bundle satisfy systolic inequality. So that's let's take it as a semi-global systolic inequality because this space is rather large in the space of all contact forms. So maybe let's make some remarks. And comment a bit on the assumptions. So first, we can weaken a bit this assumption of being invariant under a free S1 action, because very, very few manifolds carry such action, so it's rather restrictive. But we can allow, also we can allow the action to be not free, but almost free. So we can allow the existence of singular S1 orbits. The class of manifold that supports such action are called cipher bundles. And it's a much larger class than just S1 bundles over surfaces. But we cannot weaken it too much, this assumption of being S1 invariant. For example, asking just for invariance under a finite group action is not enough. Let's say invariance under any cyclic group is not enough. So meaning does not force the existence of systolic inequality. Same thing, for example, with integrability of the flow. It's also not enough to force systolic inequality. So say integrability. Of the flow. So in that sense, it's this assumption of being invariant under some S1 action is essentially optimal. So we cannot weaken it too much. So that's what makes it makes this result more interesting, let's say, than just a toy example. Let's make a few more remarks. So we have some assumptions in this theorem. And the most, maybe the most surprising one is this non-zeroness of the Euler number, so the non-triviality of the circle bundle. So what can we say? I mean, in the case E equals 0, so on trivial bundles, it's a bit unclear, but there is work in progress on S1 times S2 and on T3, which indicates that this assumption is not really necessary. So here, but it's an important ingredient of the proof. And I'm going to tell you why a tiny bit later. A last remark that I want to make is that there is a C, and C's are not completely satisfactory. So this inequality is not sharp. But now I'm going to state a second theorem, which is a sharp systolic inequalities under some more restrictive assumptions. So, theorem B, it's going to be a sharp inequality. So, we get a sharp inequality for, in the case of circle bundles over the sphere, so circle bundles over the sphere, so genus 0, plus assuming that contact forms induce a tight contact structure. So in contact topology, you have a distinction between two important classes of contact structure. Some are over-twisted, and they are very abundant. It's fairly easy to produce them. The other ones are tight. They are very rare, but they're also the ones that you care the most about if you're interested about applications. Those tight ones are the ones that you encounter in real life. See? So this sharp inequality, there are two cases, essentially depending on the sign of the Euler number. So if Euler number is negative or belongs to 1 or 2, then we have the following inequality. For all contact forms in, so we write omega 0, so genus 0, E, and I'm adding a tight exponent just to say that only consider tight contact forms. The following inequality holds. Systole square is less or equal to the inverse of the Euler number times the volume. And equality holds if and only if alpha is Zoll. Okay. I'm going to give you the second case. So second case is the following. If the Euler number is strictly greater than 2, then again we have the following inequality for all alpha in the same space of invariant tight contact forms. So Systole square is strictly less 1/2 times the volume. And here, equality is never achieved. And this constant 1/2 is optimal. Optimal in the sense that you can, for each choice of E, you can construct a sequence of contact forms in this space such that the ratio systole square over volume converges to 1/2. And maybe note that I still exclude the case E equals 0 here, as in the previous one. OK, any questions? Good. So I'm going to tell you a tiny bit about the proof and some ingredients. So let's say sketch of proof. So, yeah. Say, here, yes. For those two cases, yes.
Yeah, but for the over-twisted case, do you have some S1 symmetry? I don't think so, right?
Yeah, it can happen, yes.
Yes?
Yeah, yeah. Those, you know, this top. Sorry?
For the over-twisted contact structure,
Yes.
you have an S1 symmetry.
Yes. For example, start with any S1 invariant contact structure. You can make a loop twist in a invariant setting, you know, and you create a new family, and this is over-twisted. So you have a lot, and in the classification, almost all of them will be over-twisted. This is super small. OK. Other questions? OK. So idea of proof. Well, the first step is to construct some nice, and by nice I mean invariant by the action, surfaces of section. So construct S1 invariant, surfaces of sections. So what does it mean? When you have a flow in a free manifold, a surface of section for this flow is going to be some embedded surface in the ambient space, possibly with boundary components, possibly disconnected, why not, which has the following property, that for any choice of point in the interior of this embedded surface, you're going to follow its orbit by the flow, and the condition is that this orbit hits again this embedded surface in the future. So having a surface of section is a way, I mean, it allows you to encode a big part, let's say, of the dynamic of the flow by some surface diffeomorphism. So it's a convenient thing to have. And here we can use the integrability of the flow to construct a surface of section which is well suited, let's say, to this setting because it's going to be invariant by the action. Each component of this surface of section is going to be invariant. In general, this surface of section will not be global. It's not going to see the whole rep flow, but it's going to be big enough for the purpose of the proof. And it's going to be a disjoint union. Disjoint union of embedded annuli. OK? So that's step one, construct this, and then we have to use it somehow. So step two. Well, in the case of theorem B, those assumptions, genus 0 and tight contact structure, are the conditions that you need to make sure that the surface of section is connected. Let's give it a name, I don't know, sigma. Well, for theorem B, sigma is connected. And then everything is encoded by a unique DFO, and then I'm not going to say anything more than there is a direct argument, which gives the sharp inequality. In the case of theorem B, of theorem A, it's a bit more tricky because you don't really control the number, the size of the surface of section. You don't really know which of its component is going to estimate well the volume. You don't really know each of the which component is going to estimate well the systole, how they interact together. So you have to work a bit, and can give a proof by contradiction. So now it's going to go as follows. Assume that there is no systolic inequality for this space of invariant contact forms. And then you have to work to try to see exactly what it means in terms of the surface of section, in terms of the first written map of the surface of section. And what you can prove in the end, after, I mean, this is the technical part of the work, let's say. Let's say the first written map of an invariant rep flow with high systolic ratio, with large systolic ratio, is actually very constrained. It's going to have to be C1 close, let's say, to a uniform rotation on each of those annuli. So whatever it means that there is a very rigid model for invariant contact forms with large systolic ratio. That's one thing. So say is, say C1 is close to a uniform rotation. And now the contradiction is going to come from the fact that you can also read the Holland number of the bundle from the surface of section. And in fact, the only value of the Holland number which is going to be compatible with this very constraining property of the rep flows is 0. So I'm going to write it here. This forces E equals 0. So if you started in the first place from, well, if you know a priori that your manifold is a non-trivial circle bundle, then you know that this number is never 0, and you get a contradiction. So that's it for the proof. And maybe in the 2 last minutes, I just want to say a few words about what happens also in higher dimensions and what we should expect to hold. So I'm just going to give one proposition, because everything in higher dimension is really work in progress, but there is one thing that I can tell you, is there are S1 invariant contact forms on S5 with arbitrarily large systolic ratio. So in higher dimension, it is not enough to ask for being invariant under some S1 action, and you might want to ask, I mean, in order to force some systolic inequality, you might want to ask for being invariant under larger groups, let's say, and this is work in progress. So I'm going to stop here.